Hey everyone, in this video I'm going to be covering the start and stop states in Lyra, which will include how Lyra uses distance matching and stride warping to remove foot sliding within these states. I have the animation graph of the main animation blueprint open. I'm going to navigate into the Locomotion state machine, and here we're going to see the start state. It's connected to the idle state and the stop state. We can transition into it from the idle state if we have acceleration, or if we have the gameplay tag melee and we have velocity. The start state uses the full body start state linked layer and also applies the same rifle jog leans state as the loop state, I believe, or the cycle state. Yep. So the rifle jog leans, again, is just an additive that can be applied to any of the animation sets that allows the character to lean when they're moving in a direction and turning at the same time. So when you're holding down one of the keys and also moving your mouse to turn your camera, essentially. It's blended in with the additive lean angle, which I'll search up. Which is set in update rotation data here. There are two functions bound to the output animation pose. When it becomes relevant, a setup start state function is called, and each update an update start function is called. The setup start state sets a start direction enumerator from the local velocity direction. If you want to know how these direction variables are set, you can refer back to the first video in the series. For the update start state, it checks if the state is blending out. If it is not blending out, it sets the root yaw offset mode to hold. Now, let's head over to the animation blueprint item Anim layers base. Let's find the animation layer full body start state. Here we go. It's more complicated than the previous layers. We'll just take it one bit at a time. We have a sequence evaluator here with the explicit time and the sequence set to dynamic. There are two functions bound to it. So let's go ahead and see what they are. We have set up start anim. And this is determining a start animation from these variables. These are structs here, which contain 4 different animation slots. And based on whether or not the character is aiming down the sights and crouching, an animation is selected. The sequence is set from that animation. The explicit time is set to 0. And the stride warping start alpha is also set to 0. Well, I'll explain stride warping momentarily here. So let's come over to this here. And for now, let's just say that we have a start animation being distance matched. And distance matching is a method of playing back certain frames on an animation based on the distance traveled or a predicted distance left to travel. It's used on starts and stops to remove foot sliding, and we'll see exactly how it's used in this update function. Now let's say we have a start animation, it's playing, and it gets fed into orientation warping. Now, orientation warping is a method of rotating the legs and the upper body of the character in opposing directions so that you can cover the in-between space between 2 different animations without using a blend space for 2-dimensional ground movement. So let's say you have a forward, backward, left, and right animation for jogging, just like Lyra does. You could put those together into a blend space and then and then blend between the animations in that blend space, but that can bring in issues such as foot sliding or leg crossing. What orientation warping does is that you feed it a direction, a locomotion angle, and it turns the legs by that locomotion angle, as well as rotating through the spine so that the character remains facing forward. So the orientation warping node has two modes, a graph mode and a manual mode. You can use the graph mode and just plug in your regular direction variable, and it will take the root motion data from an animation and use it to determine how it needs to rotate the bones in that animation. If you have an animation that does not have root motion, you'll need to use the manual mode, which means that you'll have to offset the input direction. And you do this by, if you're going forward, your direction is 0, so your offset would be 0. But if you're going right, or if you're using your right animation and that's being input, and the character needs to be facing 45 degrees, that's not going to work. It's going to take a character that's facing 90 degrees and rotate them by 45 degrees. So if you're going right, you'd have to subtract 90 degrees from the input direction so that the character is rotating the correct way. And I'm going to go ahead and give you guys an example of orientation warping. Alright, here we go. So now, here I'm playing left and right facing animations, moving forward, moving backwards. These are all on-axis animations here. But now if I move it 45 degrees, we're not using a blend space, we are using orientation warping. We are either going to be orientation warping the left animation here, or we're going to be orientation warping the forward animation, depending on which got selected. And the orientation warping node is filling in all the in-betweens where the 4 on-axis animations, that the 4 on-axis animations don't cover. It is a super useful node. Now in the spine chain, Lyra also added an IK hand root bone into the spine chain so that the orientation warping does not affect the aiming of the weapon as their final spine bone. Next we have stride warping. Stride warping will warp the stride of a character. Again, it has a graph and manual mode. If you have root motion, you can use the graph mode, which is what Lyra is doing. And with stride warping, you can essentially warp the stride of an animation without warping the speed of that animation. That would be a bit harder for me to show. So if you have an animation that, let's just take a cycle as an example, because this will work on cycles as well. So let's say you have an animation, and that it is made for a speed of, let's say, 300 Unreal units a second. And you decide that you want a gameplay speed of 350, or let's say 400 Unreal units a second. Well, you could either speed up the animation, which might not look good, or you could alter the animation, create a new animation. None of those are ideal solutions. But you can use stride warping to essentially increase the distance between the legs with each step, is the simplest way to put it. But it can also decrease the distance between the legs. This is good with controllers. So if you have a range of movement, and maybe you have a walking animation and a running animation, but your input could be super tiny, you wouldn't need to play the animation super slow. The character could be taking smaller steps. So the stride warping node takes in the pelvis bone, the IK foot root, and 2 foot definitions as inputs, which contain an IK foot bone, an FK foot bone, and a thigh bone. It also has an alpha input, and it takes in a locomotion speed. Again, you can see where this displacement speed variable is set in the main animation blueprint in the first video in the series. And then that is put into the output pose. The stride warping start alpha is set in the update start anim function, which is what we're going to take a look at now. Alright, so in this function, it's setting a local variable explicit time to use further in the function. Then it is setting a stride warping start alpha. And this looks a bit complicated, but once you understand it, it makes sense. So you take the explicit time, which is the amount of time elapsed since the animation has started. See that, because this get accumulated time here. So this is just the amount of time elapsed since the animation has started. You subtract the stride warping blend in start offset. So this start offset is a setting variable, and it's set to 0.15, which means that we will not start stride warping until we're 0.15 seconds into the animation, which means that we're subtracting 0.15 seconds from explicit time. So that once explicit time is 0.15, the output of the subtraction will be 0. We also have a stride warping blend in duration scaled, which is 0.2, meaning it'll take 0.2 seconds for the stride warping to blend in. So once we've taken off the offset and we're starting to build up explicit time as we're starting to blend in, we're going to build up that time until we reach 0.2. But this output is being mapped instead of from 0 to 0.2 to 0 to 1. So it takes the 0.2 seconds, and essentially however close we're to that, if we're at 0.2 seconds, it's 1. If we're at 0.1 seconds, it's at 0.5, so on and so forth. It outputs that into the stride warping start alpha, which was used right here is the alpha input for the stride warping node. Next, we're using an advanced time by distance matching node. And I'm going to go ahead and read this comment here. This is an example of using distance matching to ensure that the distance traveled by the start animation matches the distance traveled by the pawn owner. This prevents foot sliding by keeping the animation and the motion model in sync. This effectively controls the play rate of the start animation. We clamp the effective play rate to prevent the animation from playing too slowly or too quickly. If the effective play rate is clamped, we will still see some sliding. To fix this, we use stride warping later to adjust the pose to correct for the remaining difference. The Animation Locomotion library plugin is required to have access to distance matching functions. So the advanced time by distance matching is going to take in the displacement since the last update, so the difference in displacement over the course of a single update. So it's the current update subtracted from the previous update or vice versa. I'm not sure which, and my brain isn't working well enough right now to know for sure. But you can, again, reference the first video where we cover that event graph stuff. It also takes in the distance curve name, which is just a setting variable, which is set to distance by default. And here we have the input play rate clamp, which smoothly increases the minimum play rate speed as stride warping is blended in. So we have a setting variable for the play rate clamp starts pivots, which clamps between 0.6 and 5. We break the vector, and we lerp between the stride warping blend in duration scaled, lerp that to, interpolate that to the x of this to 0.6. So we're lerping 0.2 to 0.6 based on the stride warping start alpha. Then we make that vector, and that's so that the play rate and stride warping match up. And then we have our return node, so that ends the update start anim function, and that is the full start state layer. Now let's look at the stop state. So I'm going to head back over into the animation blueprint mannequin base, go back to the anim graph, and here we see the stop state. Now we have a shared transition, which I explained in the previous video, and it takes in, well, whether we are accelerating, and if we're not accelerating, or if we are meleeing and we have velocity when we're doing so, then we are stopping. So acceleration is the way that the character moves when you have an input. When you're pressing on an input, it's applying an acceleration to the character. That acceleration value is defined within the character movement component. When you remove the input, the acceleration is no longer being applied. Therefore, friction and other things cause the character to slow down over time, which is when the stop animation is played. So we have a full body stop state and an update stop state function. So let's look at that update stop state function here. And it's fairly simple. We check for blending out. If we are not blending out, then we set the root yaw offset mode to accumulate, because we are stopping, and so we don't want to turn the camera and shift our whole character around. We're just going to remain facing the way we're facing once we begin stopping. Let's head back over into item anim layers base, and let's search for the full body stop state layer. All right, here it is. We have a sequence evaluator, two sequence evaluators, which is this hip fire, update hip fire, raise weapon pose. We'll come back to this, and we're blending these based on the hip fire upper body override weight. So I will come back to this after we look at the sequence evaluator with the setup stop anim and update stop anim. Again, the sequence and explicit time are set to dynamic. Also note that should loop is set to false. It was also set to false on the start sequence evaluator. So let's search up setup stop anim. All right, so we're selecting a sequence based on the same criteria as everywhere else. A velocity direction enumerator is being used to select from a struct containing animations of the type anim struct cardinal directions, which I believe I already covered this. In case I haven't, here it is, anim struct cardinal directions. So you have a forward, backward, left, and right direction, all of type anim sequence. And then that's the type used for these variables inside of item anim layers base. And based on whether or not we're aiming down our sights or crouching, we select, and our direction, we're selecting an animation, setting the sequence. Next, we have this section here. We take in a should distance match stop function as an input into a branch, and this checks if we have velocity and if we do not have acceleration. So if we have velocity and we do not have acceleration, we want to distance match. But if we have velocity and we have acceleration, which isn't going to be true, we're not going to be in the stop state if that's the case. So if we do not have velocity and we do not have acceleration, then we automatically distance match to the target of 0. And this distance match to target node is different because you give it a target. You're not advancing the time by the difference in displacement over a frame. You're distance matching towards a target distance. So let's move on to the update stop anim function. I was going to say let's look at the curves in one of the stop animations. We'll get to that when we get to this distance match to target node here. So again, should distance match stop? If it's true, we're going to set a distance to match by getting a predicted stop distance, which uses this node that comes with that animation locomotion library plugin, predict ground movement stop location. We're taking in variables from the values from the movement component, getting the vector length of the stop location. It doesn't output your location in world space, it outputs your location in actor space. So you get the length of that vector, and that's the distance between the actor and the stop point. And it is redoing this calculation each update and updating this distance to match each update. And as long as this distance to match is greater than 0, then we're going to distance match to target, which inputs the distance left to match, so the distance we have left. So it's going to select an exact point on the distance curve of an animation and set the evaluator to that time. And then we end the function. However, if the distance to match is not greater than 0, so if we are at the stop point, then we're going to advance the time normally once the characters come to a stop. by just advancing the time with a play rate of 1. Because there might be some recovery time after the stopping animation that'll blend into an idle that we can play as long as we're not starting. If we start moving again, then we can just blend out of stop into a start. And this also is done if we should not distance match our stop. So, I'm going to close out of these functions. We're going to come back to this. But I'm going to go over to Locomotion, unarmed, and I'm going to search stop. And let's find unarmed jog forward stop. And now I'm going to uncheck the enable root motion and use force root lock, which allows us to see the animation. And if you uncheck those at any point, you'll have to check them again, or it's going to break things while playing. The character will move separate from the capsule. And we have this distance curve, which is applied through a modifier that comes with one of the animation plugins that's enabled with the project. If we search plugins, we open our plugins window. I'm not sure why that's not coming up here. Here we go. Alright, well, I've moved that to some odd spot, but there's an animation modifier plugin that you need to enable. You'll see it enabled in Lyra. I'm not sure why that window's not coming up right now. But you can see that it goes from negative 218.747 to 0. So it's going up from a negative to 0. But you know that the distance variable is, there's our plugins. Our distance variable in our update stop anim is just the distance. It's not negative, but the curve needs to be a negative and the distance needs to be just a regular distance, a positive, for it to work properly. So now we're blending with a layered blend per bone using an upper body mask. So for the upper body, we're blending in this sequence evaluator with a dynamic sequence, which uses the update function, update hip fire raise weapon pose. So let's search update hip fire raise weapon pose. And here we see it just chooses a sequence based on whether or not we're crouching. And it's just a hip fire pose sequence. And it's blending that in with this hip fire upper body override weight float. So let's open up a find results window, and search hip fire upper body override weight. And here is that function we covered in a previous video. And we can see that here is where it comes into play. I walk through this function, or I try to. It's pretty complicated. I may have been able to do a better job of it. I might come back and replace that video once I'm further into understanding this all. But we can see here that we are calculating this hip fire upper body override weight based on a variety of things. And you can refer to a previous video for that if you haven't seen it for some reason. I definitely recommend you watch this series in order. It'll make a lot more sense if you do. So that is our full body stop state layer. We have our stops, and then if we're hip firing while we're stopping, we blend in that pose. So back over in the mannequin base, we can transition out of stop back to start if we have acceleration, or out of stop to idle if we are finished stopping, the animation is done. If crouch state change is true, or if aim down sight state change is true, or if the linked layer is changed, meaning we've changed our weapon. Now pivot can also enter stops if has acceleration is not true. We'll be covering pivots in a future video. And that is it for the start and stop states in Lyra. I'm just going to go over in here and play. I'll grab the, not the default experience, let's do elimination. And I'll just walk around a bit and try to explain and show you guys what's happening now that we've gotten far enough in. So we have the turn and play stuff we covered in the previous video. And we have our start. Whoops, which played briefly there. There's a stop, another stop, a start, and a stop. It's all very fluid and seamless. They did a great job with making this really fluid in Lyra. And I'll give an example of the root yaw offset stuff that gets blended in as we're stopping. So if I stop and turn, we don't turn until we're finished stopping. You can see that there. I hope you enjoyed or found the video useful. If you did, be sure to leave a like and subscribe to the channel. In the next video, I will be covering the cycle state and potentially some more stuff too, depending on how long that takes. Thanks for watching, and I'll see you in the next video.